This meeting is being recorded.
Hey, afternoon, everyone. Hope you managed to get some rest in yesterday. I know I didn't, but I hope better for you. So today we'll continue where we left off last time. So just a recap of what we did on Monday. What we did on Monday was looking at binary trees and later on a specialization of binary trees to binary search trees, right? So what we were looking at is using binary trees as basically a data structure that supports efficient lookup of things that are stored in the tree, and we kind of argued that if we have a tree structure, we have the opportunity to reduce the search space at each step by half, right? Rather than if we have a linear list of elements, and we are looking for something, each time we compare an element to the key that we are looking for, we just reduce the search space by 1, and we still have the rest of the list to go through. Whereas with the tree, if we know in which subtree the key that we are looking for resides, we can kind of ignore the other subtree and split the search problem into half under ideal circumstances. And we started with a general binary tree, which just has nodes which contain we use naturals as keys and strings as some sort of information that it contains, and containing left and right subtrees. And our initial kind of naive implementation used contains predicate, which checked each subtree whether it contains the key, and we kind of observed like that even though we make the decision to go into the left or the right subtree, the contains predicate actually searched one of the trees completely to determine that the key wasn't indeed there. So in the worst case, if our key was at the leaf of the right subtree, right, we would actually end up with a performance that was basically the same as a list, right? So we kind of thought about, okay, how can we get rid of this expensive contains operation, and we homed in on using an ordering on the type of keys. So in this case, we have natural numbers where we have an order that's well defined. We know whether a number is less or greater than something else. So we used actually the same structure as we had before. We just introduced a constraint, an additional constraint on our data structure, which says that if we have a tree, right, with a root and a key, with a root that contains a key, then all the elements in the left subtree need to be smaller than the key in the root, in the current root, and all the keys in the right subtree need to be greater than the current root, right? And that gives us a very quick, very easy way to determine whether we need to be looking in the left subtree or whether we need to be looking in the right subtree. And we looked at an example and implemented, we implemented the height, but we implemented a retrieval operation which made use of this property. So we either found the key that we're looking for, in which case we return the info associated with the key, or if the key we are looking for is less than, then we go to the left and search and forget about the right subtree completely. If it's greater than the current key, we go to the right and completely forget about the left subtree. So this allowed us to have a simple way of determining where we need to go, and it allowed us to kind of skip over large parts of the data structure, especially with trees that look like this, where we have a nice structure and it's kind of distributed, right? We get a pretty close to ideal performance over there. Okay, any questions about this part? About the retrieval, the principle of having some order and splitting into a left and right subtree? Okay, so where we'll go next is actually thinking about how do we construct trees that have this nice property of being a binary search trees, having this property that the left subtrees contains values that are less than, the right subtree contains values that are greater than. We kind of just assume that it exists. We have trees that fulfill this property, but now we want to look how do we actually construct this. And a use case scenario for this, imagine that you have a file, like a CSV file or a spreadsheet with some identifiers and names, right, next to them. And this is some unsorted list, maybe you sorted it, doesn't really matter. You want to read in the file, contains hundreds or thousands of elements, and you want to construct a data structure that allows you to quickly look up a name that's associated with an identifier, right? So initially you have something like a list of ID and name pairs, and we will represent this using a let me do this key info pair, right? Defining a info is a pair, and we have number. Did we use natural and string? Okay. And what we want to do is to take in a list of key info pairs and construct a binary search tree out of this. All right. So that we can read in all the information and have a way of looking up data based on the keys. So question now is, how do we go about this? We are defining make BST list of key info. So a few examples. Say they have an empty list. What tree do I expect to get back? Charlie? Just a leaf, exactly. If there's no information, there is no node for me to create, so I just get an empty tree back, right? So in this case, the empty list corresponds directly to an empty leaf. Now, let's do another example. Let's say that I have a list with one element, let's say for C, and I'm trying to construct a binary search tree out of this. Yeah, you know? Exactly. make node containing this information and 2 leaves. Right, that's the only thing. Still think about it as having the property now. If I look up 1, 2, 3, 4, can I do this from this tree? And I can very easily. It's right there at the top. Let me start constructing some visualizations of this. So what we get from here is a tree containing this and just having 2 leaves on either side. Now let's say that I extend the list with 2D, for example. So I started with an empty list, right? Having a list of one element means taking an empty list and adding an element in front of it. And if you think about it as this being the base case, right? So the empty tree corresponds to the base case of the empty list. Then here, in some sense, we took the empty tree that is the result of constructing a tree from an empty list and added 4 to it. What shape of a tree will we get if we add 1 more element to it? Yeah, Brendan? Mm-hmm.
And then after, I guess it would be like, you make another node where, then you have to decide if you go left or right. And since 4 is greater than 2, 1 goes to the right, or 2 on the right branch.
Okay, so you suggest to place what to the right of what?
So like you make another node for 2, and then the right branch of the node that has 2 numbers would be that 4C.
Okay, so you suggest to basically doing something like 2C, 2D. Being on here, and something like this. Okay, that's a valid tree coming out of this list. However, what I was trying to kind of like make you think about is how the tree that we are constructing here corresponds to the recursive structure of the list, right? When we process a list, the typical pattern of recursion is that we go all the way down to the empty case in the list and kind of start rebuilding from there. This is how most our functions worked. This is how foldr worked. Right? We build something for the empty case, then we add the 1 element and add it to it, etc. So what we would get if we process this way, right? We first construct a tree for containing just this 1 element, which means we are constructing an empty one. We add this one, we get this tree, and then we try to add 2 to a tree that already contains 4, which means we kind of flip it around and take the 4 that is returned from the previous one and try to find a place for 2 instead in the tree that is there. Because 2 is less than 4, we need to go to the left and we replace this one with a node containing 2 and 2 leaves. So what we get here is pair 2D and leaf, leaf, and leaf. So what Brandon suggested is absolutely correct. It's just the order in which we actually are inserting the elements from the list that kind of changes the things around. And it's easier to, as we process the list, to work on it this way, so adding from the last element. Let's do one more before we dig into the implementation. So let's say that I'll add another element to this one. Again, I'll copy my tree. So if we have this one already constructed, yeah?
Would that be a make node instead of make pair? Because
Yes, thank you.
you also talked about that.
Sorry? Yeah, I copied it down, so it's everywhere. Any other typos, mistakes? Thanks for catching that. So now, where does 5 end up? Yeah, Stephen? So it's the second, this one, right? Yeah, exactly. So we already constructed this tree by processing 4 and 2, so we just want to add 5 into it. We compare 5 and 4. 5 is greater than 4, so it doesn't go to the left. Instead, it goes to the right. We have an immediate leaf, so we can. That's where we can hang 5 from. And we end up here. Let me do this. And we end up with this tree. Okay. Brennan?
So then like the very top element, is always going to be the last element.
If we process the list from the right, which is probably the simplest way to think about it right now, then yes, the last element will be there. If we just have this list, right, this is not the only binary tree that is a valid representation of that a binary search tree. If I processed it from the beginning, I would have 5 at the root, right? Then 2 would be over here, and 4 would be to the left and to the right of 2. That would be another if we flip the order, and we will discuss this a little bit later on. Okay, but this is kind of what we are aiming for right now. So, how can we actually define this? Stephen? Sorry? Which template? Sorry? Can you speak up? I don't. The node template. I don't have a tree coming in here, right? I need to process a list. Okay. So one thing we could do is use the list template and simply process it that way. But another way of thinking about it is kind of thinking about, as we were going from example to example and adding elements, what was the operation that we were performing, right? Because we assumed that we had a list, that we had a tree corresponding to a previous list, and we added a new element at each point performing something. We were going through the list, adding elements, starting from the right and processing from there. Which list abstraction does this correspond to? Eleanor? Fold R. So what we were actually doing is folding from the right using some operation over our list, right? We started with the empty tree, so we started with a leaf that corresponds to the empty list. And all that's missing here is some insertion operation that actually takes a pair from the list and finds its rightful place in the tree. Okay, so this was easy. Now the only thing missing is actually writing the insert operation. So what we want here is, I'll get to you, an insert operation, which the way we are using it needs to take a key info pair from the list and a binary search tree and produce a new binary search tree. So takes in a key info and a BST and produces a BST. Whatevs. Fine, insert, and we get a key info and a BST. Okay, so now we need to use the template because what we are processing here is the binary search tree, right? That's where we we're going through the structure, finding the space, finding the right place for our key info pair. So let me copy this thing. Let's start with this. It's a good start. Okay. So we have a key info pair. In our left hand, we have a leaf, an empty binary search tree in our right hand. What are we returning here? Fiona? Exactly. So if we have an empty tree, inserting it there's only one place it can go. So we make a note from the key of our key info pair and our what did I call it? Info and empty subtrees. That's our base case. Now I think it's easier to kind of leave some room here. What do we do in the recursive call? In the node case. So we have a node with a key. We have a left and a right subtree. And we need to decide whether if I, for example, want to insert 3 right now into this tree, right? I have a 3 and I have a root node with 4. So I need to find where I want to insert it. Yeah?
You would compare the key of the key info that passes as an argument to the key of the node.
Yeah, exactly. So if I look at this and I have 3 and 4, 3 is less than 4, so it definitely shouldn't go here, because when we are retrieving, it's not where we would expect it. So we need to go to the left subtree, right? And once I'm in the left subtree, I do exactly the same thing again and compare the root node of that one to see whether I need to go to the left and the right, right? But at this point, the only thing we need to do is to find out whether we need to go down this path or down this path. So what we need is to compare the key in the pair that we get to the key in the node. All right. And here, basically, per key is less than node key, which means we need to insert on the left. Let me. And we'll have a symmetric case where if the key we are trying to insert into the tree is greater than, then we want to insert on the right. Right? So we have these two cases. Now, what does it mean to insert on the left or on the right? If it helps, try to think about the task of inserting an element to the end of a list. Right? It's a slightly simpler process. If I have a cons and I have an element and I have something that I want to insert at the end of the list, right? If I have a cons, I'm not yet at the end of the list. So what I need to do is to preserve the cons in place, because I want to keep the structure of what I saw so far, and continue inserting in the rest of the list. Right? So I know that I will have to have a recursive call here. Because that's the part where I'm finding the place, right? But if I leave this, I'm actually deleting the tree as I go through it, because I'm throwing away all the information. So what I need to do is to simply make a new node. And this is a little tedious, but I need to preserve all the information that I am not changing. The left node gets changed by the insertion operation. The right subtree stays the same. Okay. So I'm taking apart the current make node, the root of the tree, keeping the key and info in place, modifying the left subtree, keeping the right subtree in place. I'm doing that. In the symmetric case, I do basically the same thing, but instead of inserting on the left, I'm inserting on the right. Okay, so again, inserting a key into a binary search tree amounts to first two cases on the top level, right? We either have an empty tree, so we just have a leaf, which means there's only one place where the key info pair can go. We make a new node with two empty subtrees and we are done. If we do have a node with a key info, right, that means that we either need to depending on what the relation between the current key and the node key is, we either need to go to the left, keeping the current node intact, except we are inserting on the left. Otherwise, if the current key is greater than the node key, we keep the current node intact, preserve the left subtree, but insert into the right subtree. Does it make sense? Are there any questions? It's really just if you think about how would I do this for a list if I'm trying to find a place for my element. If I'm not placing it right now, I preserve the current const constructor with the current element and go down the list. Here it's just an added layer of deciding whether I go to the left subtree or the right subtree, and I insert it there. Okay, any questions about insertion? Yeah?
What happens if the
Excellent question. So what I did here was making a silent assumption that we don't have duplicates in the list that we are inserting, and that's a fairly reasonable assertion or assumption. Okay, so for a simplification, if we wanted to avoid making this assumption, we would have to choose one of these and replace them with less or equal to, or greater or equal to, right? So that we can still do this. If the key already exists, if we find the key, otherwise this would crash. But here we go to the left or to the right. Then we also have to modify our retrieve function to actually, the retrieve function doesn't need to be modified. What it will mean is the oldest element will be retrieved first, because that's the one that we will find first. All right, if that makes sense. Yes?
would that still be a valid binary search tree?
Excellent question. So I would need to modify my kind of constraint. It would still be a valid binary search tree depending on how we want to use it. Okay. Another solution is adding an extra case. So something like this. In node, if they are equal, I can do a simple thing where I simply replace the information that is stored in this key in the current node. So that's also a valid thing. Again, depending on how you want to use your data structure, I can actually change the current node, the info that it contains, and leave the left and right nodes intact. Therefore, in effect, erasing the previous information from the tree. Okay. Again, it depends on how you want to use your data structure and if this is a valid operation. Okay, I will keep the assumption there. Because all these things are kind of considerations that you need to make when you build your binary tree data structure. I just want to, just like with insert, we assume that the key is not already in the tree. On the level of make BSD, we need to assume that there are no duplicate keys in the given list of key infos. Now, let me try if this actually runs. And it does. Okay. Any additional questions about this process? Okay, so What I want to think about for a little bit now is what the relationship is between the order of elements in the list that is that we get as input to make BST and the tree that we get as output. And Brandon asked a good question about it. So what we got here, right, was a nice, I don't know if I mentioned the terminology, but this is what we would call a balanced tree, right, where kind of the both sides kind of look the same. There's a formal definition for it that I will mention later, but basically we are aiming for something like this, because then any element is almost at most the same distance away from the root, which is what we want. I want to compare these two cases here now. So we have two lists, right? And the only difference is that this one is actually this list reversed. Okay. Otherwise, they contain the same elements, and I want to take a look at what kind of trees do we get just based on the ordering. So I'll do a little bit of ASCII art here. So if we process this list using make BST, what will be the root node? Yep, 4E, exactly. So that will be the root node. It's the last element. Okay, then we have 14D. Where does it go? Yeah, Brennan? To the right, because it's greater than 4. So we put it right here to the right. 7. Charlie? To the left of the 14, so we go right, then left. That was C. 12. Where does 12 go, Stephen? To the right of 7C, exactly. So 12 is greater than 4. It's less than 14, so it goes to the left. Then the 7, 12 is greater than 7, so it goes to the right. B, and finally we have 10. Where does 10 end up? Fiona? 10 goes to the, yes, 10 goes to the left of the 12. 10 is greater than 4, so we go right. Less than 14, so we go left. Greater than 7, so we go right. Less than 12, so we go left. And we end up with this kind of tree. And finally, okay, what is the height of this tree? Josh? Sorry? Length of the list, exactly. We have 5 elements in the list. The height of the tree is the same as the list, so the height is 5, meaning that the worst case performance for looking up an element here is actually the first element in the list. Takes 5 steps, okay? Incidentally, the worst case performance for the list is the best case performance for the tree, because we find it immediately. So this tree really isn't ideal, right? On average, we have about the same performance as a list, because we don't make use of we don't distribute the elements. Okay. Now, let's look at the second list, which has exactly the same elements. And let's build a tree out of this one. What's the root? Yeah? 10A. It's the last element, meaning it will be the first tree that we construct. What's the next one and where does it go? Yeah?
12C and the first
Yes, exactly. 12B going to the right. What is the next one? Bren?
7C goes to the left, 9A.
Exactly. So we go to the left. 7C. Branches. What's the next one? Charlie?
14D returns to the right of 12B.
14D, we go to the right and to the right. 14D. And the last one, Fiona?
4 goes to the left.
Left, exactly. So we go 4E right about here. And we have a leaf here, leaf here. And a Okay, what's the height of this tree? Yeah? 3, right? Instead of 5, which was this case, just by flipping the order of the list, we got a completely different shape of a tree, right? Right here, we have, for our purposes, a variation of the worst shape that we can have for the tree, right? Basically just a list and we just zigzag trying to find the element. Here we have a completely balanced tree that is evenly distributed around the root node, right? Any element is at most three steps away, right? Going from 5 to 3 doesn't seem like such a great achievement. But when you are distributing a list of 1,000 elements, right, then there's a difference whether you have 1,000 elements going to one direction or you evenly distribute them. I cannot do logarithms off the top of my head, so I cannot really tell you what the height is of that one, but it's 1024. Well, whatever. Okay. Now, what is the relationship between the list and the tree that we get in as an output? What happens if we are inserting a sorted list, for example, and making a tree out of it? So that seems like something that maybe would be kind of ideal, right? We have a sorted list, we start inserting, you know? Yeah. So what we end up is just a twig of things just going in one direction. So we are taking one list and just making it into a tree list, right? So a sorted list really isn't the best thing. What is the best thing? Yeah?
The parent node would be like the middle node, the middle pair. And then you just have people on the side.
Yeah, exactly. So if we start inserting with the median of the list, that's where we get the ideal performance, right? Because that's the middle of the list, and that means that the elements will be evenly distributed to the left and to the right, right? Then when we want to insert on the left, we need to take the median of all the elements that are less than the root element and insert that one. On the right, we need to insert the median of that one, etc. So actually, if you have a sorted list, the best approach is to take the middle element, insert it as a root, then take the middle element of the lower list, insert it as the left one, etc. You get the picture. Okay. And actually, as you will, I think, learn in algorithms and probably in Fundis too, having a list that's already organized like this, like having the median first, then having the median of the lower part as the second, and median of the right part of the second, is actually a representation of a balanced tree. Because you can always, the root node is the first element, the left root node is the second element, the right root node is the third element, and then you kind of can find your way around the list, which is kind of cool. You have a very efficient linear representation. Josh?
Besides having the last element what other requirements do you use to get values? It seems though, as long as the variable is the median, everything else should follow.
So, not everything, because I can pick a median here, which means if I just pick the median as the first thing, still means that I can have kind of deformed trees. Well, deformed is not a good word, but kind of trees that are twig shaped or linear on the left side or on the right side, right? I just pick the median here, which means that, okay, the elements will be evenly distributed on this side and this side, but I still don't get the nice, might not get the nice property for the rest of the elements, right? So the property really is that every root node needs to be the median of its respective side of the tree, right? So it's kind of a recursive property of the tree, if you want. Okay. So formally, actually, a balanced tree is a tree that has the property where basically the distance on any level, any subtree, the distance between the two leaves or the distance to the leaf on either side is at most differs by at most 1. Right? So if I take away this 14, it's still a balanced tree over there. Okay, so that's kind of the formal definition. And let me just this, check that everything works, and it does. Okay. Any other questions about binary trees? This is kind of a quick overview. There's much more to this topic because you can have your binary tree, you can have the data structures that are called self-balancing trees. So every time you insert, the tree actually rearranges so that it keeps the balance property, right? It comes at a slight cost, meaning that every time you insert an element, you might be performing a more expensive operation there. So it's again, like with everything in computer science, it's about trade-offs between what you want to do. There's no perfect solution. Okay. Okay, if we're okay with binary search trees, what I want to talk about for the rest of the lecture is tree abstractions, right? And what I want to consider is just like when we had lists and we started with things like lists of numbers, right, and lists of strings, and then we wrote functions for one and functions for the other one, and then we observed actually they are exactly the same thing. They just differ by a few places. So let me get kind of two motivating examples. So the first one is a binary tree. We remove the info node, so we just insert numbers in this case. The structure is still the same. We have a node with some value. In this case, we say that the value is a number, so it's a binary tree of numbers. We have a template, which is kind of as expected. We have leave, node, do something with the value, and recurse over the left and right subtrees, right? And now let's say that I want to write a function that squares all the numbers in the tree, right? The same way we were squaring all the numbers in a list. This is an operation that makes total sense. We have numbers in the nodes. We want to square all of them. So the thing that I do, of course, is use my template, right? What do I return for a leaf? Charlie? Just a leaf. No number to square. Keep the thing. What about a node? Fiona? I square the value. I call the square function on the left and the right subtree. Okay. And just like with going through a list, I keep the structure intact. So that means that I need to reconstruct the node, right? Just like with a list, the only difference is that we have two recursive calls. If we have a leaf, leave intact. If we have a node, we have a number that we square, and then we square all the numbers on the left and all the numbers on the right, keeping the shape of the tree the same. Okay, let me do an example just to see whether I succeeded. Let's do 4 and okay. So if I square this tree, what I should get back is square of 1 is 1, square of 2 is 4, square of 3 is 9. This is leaf, square of 4 is 16. And that should be it. Let me run this. And we're good. Okay. Everybody clear on how this function works? Okay, now let me show you a completely different data type, which is a binary tree of strings. Right? To make it obvious how different it is, I'm still using the same struct that I defined before. But I'm saying that it contains a string. I have my template, right, which is very different than the previous one. And I want to write a function that takes a binary tree of strings and returns a binary tree with all the lengths of the strings that are in the respective places. So again, I do my little exercise here of copying the template. Right? Empty tree, leaf. All we can do is just return a leaf. Now, what we wanted to do is to take the length of the string in the node. So that's the operation that we are applying here. Found the string, take its length, keep it in there. Recur on the left and right subtrees. And just like before, we preserve the structure, so we simply make a node. Node of this. Okay. Very different than the previous one. Let me give some examples. Make node something. And I would expect something like, okay, so structure stays the same, which means we'll have the same shape. Hello is 5 long, and no is just 2. It's 1, 2, 3, 4, 5, 6, 7. So 11, if I'm counting right. We should get something like that. Ooh. I'm not counting right. How is it? What? Well, of course. Otherwise, we're good. Okay. So again, we're just applying an operation to each value of the binary search tree, and now we can look at the two data definitions, right? And we can spot the difference, just like we did with a list, right? Both of them have leaves that are empty. Both of them have nodes that have 2 recursive calls to themselves. The only place that they really differ is what element they carry. Which means this is an excellent candidate for abstraction and saying a bt of x is one of, right? It's either a leaf or it's a make node containing something of the type x and a left and right subtree with the same values, right? Abstracting the data type that is contained within the tree, expressing just that the shape is there. Now, the template, of course, is exactly the same as both of those. It just maybe should change the name so they hint at more general structure. Okay. Does that definition need a key? Okay, so maybe I kind of abandoned the binary search trees a little bit too quickly. So now we are not thinking about binary search trees. We don't have the notion of keys anymore. Right now we are just looking at binary trees that simply contain some data, right? Some arbitrary stuff. Just like we had a list of X, we are building a binary tree of X. Okay. And of course, a binary search tree can be represented using this data type simply by putting pairs of keys and info as the information here, right? Then it even directly corresponds to the list that we were building it from. Make some of our code a little easier. So we have the same template Nothing really changes there. And now we get to spot the difference with the two functions that we defined. So if I take this one and I take my string one, where do they differ? Yeah?
Well, they differ in what they take, once they get over this.
Mm-hmm. Okay, so they differ in the signature, right? One of them takes a binary tree of numbers, the other one takes a binary tree of strings. They both happen to return the same type of binary tree. But the important difference in the code is the operation that we apply to each of those elements. So this seems like a good candidate for abstraction. What does this pattern remind you of? Charlie? It's a map, right? We take a data structure containing some elements, we take a function, and we apply that function to each element in the data structure. Right? So what we are building here is actually a binary tree map. Now we'll leave the signature for the end. So let me take one of these and just start abstracting. So we're building a BT map. We are taking a BTX. Right. These the leaf case is the same between the two functions that stays in place. In both cases, we are making a node that contains a recursive call on the two subtrees. So this means that our map function will need to recur as well. Okay, and then the next thing where they differ is this operation. So square here, string length over here. So that means that this is a candidate for abstracting. So our BT map needs to take an operation. And we're done. Right? Just abstracting the only real difference in the code, which was the operation that we are applying to be an argument to the function, leaving the structure of the rest in place. Of course, I need to rename a few variables, but it captures the pattern that is in both of these functions. Now, what is the signature of this? So here we have the first argument is some function, right, that returns something and returns something else. The first argument is a binary tree of something. So of some x, and we are returning also a binary tree of something. Yeah? So we are taking in a binary tree of x and returning a binary tree of y. And of course the x and y is determined by the function that we pass in. If we are using a squaring function, we are converting a binary tree of numbers to a binary tree of numbers. If we are taking string length as the operation, we are converting a binary tree of strings to a binary tree of numbers. So what we get here is this nice generic signature, right? Give me a function from x to y and I convert the binary tree of x to a binary tree of y for you. Okay, just for comparison, Here's the signature of our list map. Right. Apart from what the actual type is, it's exactly the same principle. Okay. So unfortunately, we're out of time. So what I don't get to do is to redefine these two functions as simply an abbreviation for map. So you can do that on your own. But what I would also like you to do is to think about what other list abstractions can carry over to trees and how could we implement them. Okay? Because not all of them are as straightforward as maps. Okay? Are there any questions that I can answer? All right, thank you so much for coming. I feel like a lot of you have an exam today. So good luck with that. I hope it all goes well. Have a great weekend. I'll see you next week. Thank you.